so 17.1, just introducing the terminology, vector fields. Okay, so vector field, it's something simple. But to define it properly, we need to go through a couple of definitions. Let me try to go quickly through these definitions because they're only useful in defining what a vector field is, at least for now. But so, in some sense, they're not that important to you. But here we go. Okay. So, first definition: neighborhood of a point. X in R2 or R3, doesn't matter. Rn. Okay, so when we say a neighborhood, and we usually denote it by n, say Rx, neighborhood nRx, what we mean is basically just any points. So actually, let me call this point x0. So we mean all points in R2 such that the distance of x to x0 is smaller than r. The distance of x to x0 is smaller than r. And the distance, you recall, is the magnitude of the difference. Magnitude of the difference, and so geometrically, all this is a ball. Okay, right? It's right. If this is x0, we're looking at all x whose distance from x is less than some radius r. Right. So there's some distance r, and we're looking at everybody whose distance from x0 is smaller than r. Right. So it's geometrically it's just this disk without the edge, the disk without the edge, the open disk. Okay, number two is the notion of an open set. I think we mentioned this earlier. I said we weren't going to define it, but now we are. So open set E in R2, say. We call E open if every point x in E has a neighborhood nRx contained in E. Okay. So this abbreviation is neighborhood. So let me give you an example of a non-open set. If I say, for example, the upper half plane including this line. Okay. The upper half plane including this line, okay, including the boundary, then that's not an open set, right? Because although these points, for each of these points, certainly I can find neighborhoods that are contained in the set. For anybody on the boundary, I can't do that. No matter what neighborhood I take, it's not contained entirely in the set, in my set E. Okay, so this E is not an open set. Okay. But if I took its complement, if I took this part down here, then that would be an open set, right? Because every point in here I can surround by, I'm not including the boundary in that case. And if I take a point in here, then I can put a disk around it, an open disk around it that's contained entirely inside. Okay, right? Or for example, right, an open ball, right? An open ball is also an open set in that, right, if I take any point inside, well, I can find a neighborhood centered at that point that's contained inside the set. Okay, so these guys are called open sets, okay. And the complements of them are called closed. So, are called closed. closed. You don't need to know that. Yeah, but this leads to the problem that if you consider, for example, well, forget it. I'm not going to Okay, open set. Third notion, path connected. Path connected set. Okay. So all this means is that for any 2 points, x and y in your set, there exists a path from x to y lying entirely in the set. Right? So if I have a set like this, right, the set, here's my set, E, then this is not path connected, right? Because I could take my x in here and x in here. So here's a non-example. Right? You can't have something like this, right? Because there's no path. I can't get a path going from here to here that stays entirely within the set, right? But you could have something like that. That'd be fine. That's path connected. Given any 2 points, you can find a path connected. Okay. And then the last notion, the last definition is the one that we need, the notion of region. So we call something a region if it's open and path connected. Okay. So open path connected set. Okay. And with that definition, we can now define properly, give our definition of vector field. So so let G be a region, that is to say, an open path connected set. Right. And let V go from G to R2, taking xy to V1 xy, V2 xy. Where these guys, V1 and V2, are called component functions. Okay, it's component functions. If V1 and V2 are continuously differentiable, that's what we denoted as C1. We call V a continuously differentiable vector field. So a vector field is just something that goes from a region into R2, right? So you have some region, and you have a map from that. You have a map V from there into R2. Okay. So right. So to every point in here, it associates some vector. So to every point, it associates some vector. That's called a vector field. Right? Every point gets associated some vector. A map from R2 to R2. Okay. And if these guys are continuously differentiable, then we call it a continuously differentiable vector field. So you can visualize the map like this, right, as associating a vector to every point. But what people normally do is to draw the vectors directly on the region. So people normally will visualize, you'll see pictures of vector fields like this. So at every point, they'll give the vector, right? So like maybe this vector goes to here. So we're gonna just draw that vector here, and at every point we draw the vector that's that. So that the vector field, you can just represent it directly on the domain. Okay. That maybe gives you a better image of what it's doing. Right? The vector field could be like the velocity field of some fluid. Right? You've got some fluid, it's moving around. Right? At each point, each particle has some velocity vector. Right? And you put the velocity vector at each point, and that represents the motion of the fluid.
Does it have to be continuously differentiable?
No. So if right, so you could say it like this. Maybe it's more honest to say it like this. We call a vector field. We call B a vector field, and if these things are continuously differentiable, we call it a continuously differentiable vector field.
Okay.
So a vector field is just something that associates to each point in a region vectors. Okay. And then if there's some smoothness to that association, then we say it's smooth. We call it vector field smooth. Okay, so in fact, you've already encountered some vector fields when we encountered the gradient. Right? You recall, you had some function going from R3 into R, right? And then we created this thing, right? So example, f of x, y, z is, say, e to the x cosine y, z, right? And then we created this thing called the gradient, right? The gradient, what was that? You recall, it was a vector consisting of the partials with respect to the variables, right? F with respect to x, f with respect to y, f with respect to z, right? In this case, we get with respect to x, we get dx cosine yz. With respect to y, we get u dx negative c y yz times z. And then here we get negative y e x sine yz. We'll move the z to the front here. Z. For example. Right. So what was this thing? Well, you see that to every point it associates every point x, y, z. It associates a vector, right? Every point in R3 it associates a vector in R3. It's a vector field, right? This thing was a vector field. And we give a name. We give a name to this group of vector fields. So these are these fields that arise as gradients are kind of particular. So we give them a name, gradient vector fields. F goes from R3 to R3, a vector field. If there exists a v, if there exists a function v such that the gradient of v equals f, then we call f a gradient vector field. Or a conservative vector field. And we call v a potential function for f. what I've written is actually not quite right. In fact, one puts this condition, rather that you say if there's a v such that negative the gradient equals f, then we call blah blah blah, and we call v the potential function. But certainly, if there's a function whose gradient is f, then there's a function whose negative gradient is f, namely negative the function, right? So this doesn't change f being if f is a gradient field under the previous statement, it's still a gradient field under this statement. Okay. The main thing is that you want the potential function to be the one whose negative gradient is f for physics reasons. Okay, and we'll see an example of that in a second. Okay. So you might think, why do you want negative the gradient to be f? Right? F is supposed to be the gradient field. Why do you want negative the gradient? It's okay, right? If it's negative the gradient of some field, it's going to be positive the gradient. If it's negative the gradient of some function, it's going to be positive the gradient of the negative of the function. So it's still going to be the gradient of some function. Don't worry. Right? Is what I'm saying making sense? Do you understand what I'm saying? Am I just talking to myself? No? Anyone confused by what I'm saying? Ask. Okay, good. Right. Okay, so what we see is that we've actually seen vector fields before, gradient vector fields, and so there's a whole bunch of fields that arise as gradients of functions. Okay, so you might ask, right? Are all fields conservative? Right? Are all vector fields conservative? Do they all arise as derivatives, as gradients of something? Right? And the answer is no. For example, if you consider f of x, y being y negative x, and you say, can we find a function f such that f sub x is y and f sub y is negative x? Is there a function whose derivative with respect to x is y, and whose derivative with respect to y is negative x? Right? If you think about it, well, if the derivative with respect to x is y, then you could think like this, right? If you take fxy, what's that? 1, right? If you take suppose we take further derivatives. Okay, we take this and then we further differentiate it with respect to y. You get 1. Right? If you take this and differentiate it with respect to x, you get what? Negative 1, right? So at least if the function, we can't find a twice continuously differentiable function for which this happens, because for a twice continuously differentiable function, these mixed partials should be equal to each other, right? So at least there's no twice continuously differentiable function for which this happens. Right. So maybe this. So anyway, the answer is no. The answer is no. And we'll see more of those shortly. Okay. So here is a cool example of a conservative field. So it's a physics example. So you have a mass m sitting at the origin, and you have a little mass, little m, at position x, y, z. Okay. Then the gravitational force exerted by M on M is given by the following expression, negative G M over XYZ squared, XYZ. Right, the gravitational constant times the product of the masses over the distance squared. Right, this is the inverse square law. Right, over the distance squared, and this negative here, you want to think as coming from here. Negative the vector, negative the unit vector towards the position, right? So this thing here is x. This vector here is xyz, right? You take the unit vector in that direction, and then you reverse it, right? So this is what this is saying is that it's the gravitational point force exerted is in this direction, right? It's in this direction back towards the origin, right? This is its direction, and this is its magnitude here, right? The magnitude is proportional to the product of the masses over the distance squared. So this is the gravitational force. In fact, if we let V XYZ be negative G M over XYZ's magnitude, it's an easy calculation to see that negative gradient V actually is F. In other words, the gravitational force, the gravitational field is a gradient vector field, right? F is a gradient vector field. Right? So we actually live in a gradient vector field. Right? You didn't know it, but that's the example. If somebody asks you, well, do you have an example of a gradient vector field? Well, say, what are you living with? Okay, so here's the cool, I'm using the word cool twice, cool physical digression, the law of conservation of energy. Okay. Okay, so here's the setting. You have a mass, let have a mass M in a gravitational field. F, and the position is RT. Position at time t is RT. Okay. We define energy as energy at time t is going to be 1/2 m times the magnitude of the velocity vector squared plus the potential function evaluated at that position. Right. So this first part is the kinetic energy, right? 1/2 mv squared. Those of you who've seen physics, right? 1/2 m times the velocity this times the speed squared, that's the kinetic energy of the object, plus the potential function evaluated at that position. So this is the sum of the kinetic and the potential energy. So kinetic energy plus the potential. Okay. Let's take the derivative. Let's take the derivative of that. Okay. Well, let me write it in a slightly different form. So I'm going to write it like this: 1/2 m r prime t dot r prime t plus. Okay. And now let's take the derivative. Okay. So what's the derivative? What happens when we differentiate this first part? I'll give you a minute to differentiate. Take 1 minute and differentiate. You should be able to just tell me. No, I'm not going to give you a minute. Tell me, what is it? What's the derivative of the product? A dot product of functions, right? Peter?
Is it just the product rule?
Just the product rule, right? Take the first guy, dot it against the derivative of the second guy, plus the derivative of the first guy, dot it against the second guy. Right? So you get 1/2 m, first guy dotted against the derivative of the second guy, plus the derivative of the first guy dotted against the second guy. What happened? Do you get nervous? Your minds went blank. That's okay. Happens to me as well. In my other class, I said maybe I should reserve like 1 time per semester. I'm allowed to run out of the room in a panic. Okay, so so we take the derivative there, right, and then we take the derivative of this thing, right? So the derivative of this thing, right, is going to be, by the chain rule, is r prime t, right? The derivative of v evaluated of r of t times r prime t. And so what do we have here? We have these two things are the same, right? Because right, you can commute the dot product. So we get 2 of them. We get 1/2 of 2 of them. So we get 1 of them, right? M r double prime dot r prime dot r prime of t, right? Plus the gradient of v r t dotted against r prime t. Okay. Okay. Does anyone see something nice that happens? Here we have m r double prime. Right. Can you say anything about m r double prime? From a not from a calculus point of view, but from a physics point of view. Force, right? Mass times acceleration, right? Is going to be the force, right? And so the force, we know that this force actually is negative the gradient of v, right? Our field is a gradient field, right? So it's negative gradient of v, right? And so what do you get? You get negative the gradient of v, we get 0, right? Negative gradient of v dot r prime plus the gradient of v dot r prime, and that is to get 0. Okay. So that is to say that if you take the kinetic energy plus the potential energy and differentiate it with respect to time, you get 0. In other words, energy is conserved. Okay. Any questions about that? So that's I hope you like that. That's pretty cool. Okay.
But you
Yes.
said E is constant.
Yeah.
But isn't it just, can't it change? It's just, but it's conserved. But can't the energy be, like, can't it change? So it's just constant. Oh, are you just, okay, never mind. I see. Like if you take the derivative of 1, it's 0 because it's a constant. Okay.
Yeah, it's a constant
Yeah.
function. Yeah. Okay. In this section, there are a bunch of problems that I don't think are particularly interesting, but they run along the following lines. So in my notes, you'll see it says stupid skill. So given a conservative f, what is u such that f equals the gradient of u? Yeah, this is not a particularly exciting skill. So maybe I should say it's boring rather than stupid. I'm just going to erase it entirely. Why should I make this comment? Yeah. If those of you who have seen the bingo game on my door know that one of the squares is disparaging comment about the material, or disparaging comment about the textbook. You can now X that out. Apparently, in my other class, they were playing this. They copied the bingo game. I have a bingo game on my door. They copied it and were playing it in class, and got a full line. Okay, so it's this sort of problem. Somebody gives you a vector field, y cubed plus 2xy, comma 3xy squared plus x squared, and says, they give you the fact that this is a gradient. This is the gradient of some function, and then they want you to figure out what the function is. So what is u? What is u? And so, right? What information do you have? You know that partial with respect to x is this, right? You know that the partial with respect to y is this. Okay, so let's start from one of them and figure out some information. Right? U sub x is y cubed plus 2xy. That tells me that u must look like, if I integrate this thing with respect to y, if I anti-differentiate this thing with respect to y, right? I get y cubed x plus x squared y plus some possible other function of y. Right. So anti-differentiate with respect to x. Right. Then I get this, and plus something that possibly depends that some function of y. Because if I differentiate this with respect to x, then I get the above. Right? I'm going to get y cubed plus 2xy plus 0. Right? This is like the constant. Okay. Now, if I do differentiate that with respect to y, right? So then that tells me that u sub y then is 3y squared x plus x squared plus g prime y, right? But I know already that that u sub y is 3xy squared plus y squared, right? So that tells me that g prime y is 0. In other words, g is a constant. Some constant. Okay. So putting that all together, that tells me that u xy is y cubed x plus x squared y plus some constant. Okay. There could have been a function of y there, but when we work it out, it turns out that that function is a constant. But we know already that u sub y is this, right, from here.
How come you didn't anti-differentiate u sub y?
Could have. Right, we could have started from there.
So you only have to do one of the two.
Yeah, I mean,
And then-
we could have anti-differentiated here, so that say that u is xy cubed plus y x squared plus some function of x, say, right? And then differentiate that with respect to x, we get y cubed plus 2xy plus g prime. And again, we would see that g prime is 0, so this is some constant. We could have gone the other way. Either way is will be fine. Okay. Why don't you try one? F of xy is e to the 2x plus 2x e to the 2x, comma 1. So try and figure out what this arises as the gradient of. Okay. Who can tell me what? Right. So we want u such that partial with respect to x is e to the 2x plus 2x e to the 2x, and so that u sub y is 1. So did anyone make some headway? If we integrate, if we anti-differentiate with respect to x, then what do you get? What do you get for this? Anyone get it? Yeah, Peter.
X e to the 2x.
X e to the 2x, right? X e to the 2x. Right. So this will be x e to the 2x plus some function of y. Right. And then we differentiate that with respect to y, and you get g prime y. Right. G prime y is 1. That tells us that g of y is y plus a constant. Right. And so, putting it all together, we get u xy equals x e to the 2x plus y plus c. Okay. So there's nothing, nothing particularly exciting about this, as long as you can integrate. Okay. It's basically just this is not deep stuff. Okay. Any questions? Questions? No. Should I go faster? I can go faster. Should I go faster? Close your eyes for a second. Raise the finger if you want to go faster. Okay. Raise the finger if you want. Oh, sorry. Keep your eyes closed. Raise the finger if you want to go slower. Okay. Everybody open your eyes. Thank you. Okay. So there's actually there's a fair number who want to go faster. That's good. Okay, great. So, 17.2, line integrals. So there's a lot of ideas in this section, but they're all pretty simple ideas. So let me just say that up until this point, whenever we've integrated a function, the domain of integration has had the same dimension as the dimension of the domain. So, like, if we have a function, if we have a function on, if we have a function from R to R, then when we're integrating the function over AB, right, we're integrating the function over some line, right? That line is a one-dimensional thing. Right? That segment is a one-dimensional thing, and we're integrating it. The function itself is defined on a one-dimensional thing, right? But what we're going to do now is something different. So we'll have a function defined on, say, space, say, and we'll integrate it on some, right? So the function will be on space, but we'll integrate it on some surface that lies in the space. So we'll be integrating it on something that's of a lower dimension than the full domain. Okay. So we'll be integrating functions on paths. We'll be integrating functions on surfaces that lie within higher dimensional spaces. Okay. So things are a little bit different from here on in. Okay. So first idea. So line integrals are functions along plane curves. Okay, so recall the smooth curve. So everything's going to come together now, right? We're going to talk about, we have these curves that we talked about in the first part of the course. A smooth curve, R from AB into R squared, right? Say R takes t to x of t, y of t, satisfies that 1, R prime is continuous, and 2, R prime of t is never equal to 0, is never the 0 vector for all t. Remember, we had these things we called smooth curves, right? The derivative was continuous, and it never stopped moving, right? Okay. Here we have a definition. So R, a smooth curve. Suppose you have a smooth curve, and f going from R squared to R, a function. Okay. So you have f, right? F, a function on the plane, right? And R, you have a curve that's walking around in the plane. Okay. Okay. So, okay. If the limit of these Riemann sums, summation f of xi dot yi star delta s, I goes from 1 to n goes to infinity, exists, then we call that number the line integral of f along the curve C. So here's the curve C. And so we're going to define this thing, the line integral, by using Riemann sums. Here's the picture, right? A to B here. We divide this up into n pieces, right? We partition this thing into n pieces, and in each subinterval, right? In each subinterval, we take, some sample point, right? Right. Okay. So then we use that to chop up. Right, we use that to chop up our domain here, right? So we chop up this domain, right? I'm sorry, we take the sample points here, right? And then evaluate the function at each of the sample points. So it's sort of like this. It's sort of like you have a fence, right? Right here, and you are trying to find the area of that fence, right? So at each sample point, you take a height, right? You take a height, you multiply by the arc length of that part. So this thing denotes the arc length of the subcurve. Arc length of that little bit of curve multiplied by the function at that point. That gives you some approximation. Right? And then you add all those things together and you get an approximation to the integral. You take the limit as n goes to infinity, and if that limit exists, then you call that thing the line integral of f along the curve. Okay. This is basically just like taking an area, right? Just like one dimension, right? You chop it up, you take approximations, and you add together. You take the limit. Same thing here, except that we're just doing it along a curve rather than on a straight line. Okay, so that's the definition, and then next time we'll talk about how to actually calculate these things. Okay, that's it.